Thank you, Yuanbo. Next up, we have Rupak Majumdar from MPI. Rupak is going to tell us about another decidability result of the following problem. So you're given a multi-threaded program. Each of the threads are supposed to be recursive, and you're supposed to check whether the set of behaviors which are context bounded are within the language of some within a language specified by a context-free language. So I think with that, the floor is yours, Rupak.
Right. I'm going to talk about this problem of context-bounded verification for context-free specifications. This is joint work with a number of colleagues at MPI. And this is my first POPL talk, so please be kind. Right. So the problem that we're looking at is called the refinement problem. So you're given a program, and you want to check that all the behaviors of this program belong to some specification. And we take a language theoretic perspective. So we think of the program as a generator of traces. So the program itself, the semantics of the program is given by a language of traces. And the specification is given as a language of the allowed traces. Okay, so imagine that the program is running and then there are some observable events. So when the program finishes execution, you have a word over this alphabet. And you want to make sure that every word that the program generates is allowed by the language that is the specification. So for example, your program may be generating events that are sequences of lock and unlock operations. And the specification could say that, well, lock and unlock should alternate. Okay, and that's a regular language. Now, what are the program models that generate these languages? So we're in particular interested in concurrent settings, where the program consists of a number of threads that's sharing some memory. And you can imagine that all of these threads are generating these events, and the word that you get is the interleaving of all these events that you get when you run all these threads. And unfortunately, this problem becomes undecidable very quickly, because as soon as you have two recursive threads that communicate over some finite state shared state, you can get a Turing machine. So what people have done is come up with under approximations. So in some sense, what you want to do is find a parameter k, such that as k increases, you get more and more behaviors. And essentially, instead of asking whether the entire set of behaviors of the program belong to the spec, you ask the under approximation question whether all k-bounded behaviors belong to the specification. And of course, there's an art in choosing the right parameter k. Well, you would like to have that as k goes to infinity, you recover all possible behaviors of the program. But in general, what you would like to have is that if you fix the k, then you can do an algorithmic check for this refinement question. And k should be a natural bound in the sense that, well, most behaviors fall under a small value of k. Okay, so this brings me to the first phrase in the title of the talk. What is this context-bounded refinement verification question? So the program model is multi-threaded shared memory programs, and the context-bounded refinement problem, which was introduced by a very seminal paper by Charles Kadir and Jakob Rehoff in 2005, says here's the parameter k that we talked about for under approximations. Think of a multi-threaded program, and imagine that the k says how many times can a particular thread be swapped out by the scheduler. Okay? So in particular, you look at all those traces that are possible when you execute this multi-threaded shared memory program, where each thread is context switched at most k times. And Kadir and Rehoff looked at the reachability question in this context-bounded setting. They said, well, if I give you a program and I give you a k, can you check whether there is a k context-bounded run that reaches a particular shared state? And their result was, well, for a fixed number of threads, and if you give this k an unary, then this reachability problem is NP-complete. And since then, there has been a lot of work, both theoretical and applied, in using this kind of context-bounded reachability as a way of generating good under approximations of behaviors of programs, mainly for bug finding. Okay. So what we're going to study in this talk is the context-bounded refinement problem, where our program model will be something called a multi-pushdown automaton. So you can think of this as a theoretical model of multi-threaded programs, where each thread is given by a pushdown automaton. And we'll look at all k-bounded traces of these programs. Okay, so think of these multi-threaded programs as running, but each thread can be swapped out at most k times for this parameter k. And in general, most of the work in refinement verification has looked at specifications given by regular languages. And in fact, you can reformulate the result of Kadir and Rehov in this context-bounded refinement problem for regular specifications. And essentially, without too much worry, you can show that their same result kind of holds, right? So you can show that for a fixed number of threads, given this parameter k, and a fixed regular specification, the refinement problem is coNP-complete. And the reason is that, well, you can take the refinement problem, complement this automaton, take the product, and you have a reachability problem. Okay? And the reachability problem is NP-complete. This is kind of the complement, so it's coNP-complete. So this is what we knew. So what's new in this talk is that we'll try to look at specifications that go beyond regular languages. In particular, we look at subclasses of context-free languages. Now, if the specification is context-free, you cannot do that much because you know that the universality problem for context-free languages is already undecidable, right? So you can get undecidability very quickly if you ask for the entire set of context-free languages. So what we do is we look at a subset of context-free languages given by these Dyck languages, right? And in the last two talks, you already saw the definition of Dyck languages. These are languages of balanced parentheses with t different kinds of parentheses. So this is what we're going to study. And what we show in this paper is that, again, in the same setting as Kadir and Rehov, you have a fixed number of threads, you fix the context bound, but your specification is given by a Dyck language, and this problem is also coNP-complete. So in other words, going from just regular specifications to Dyck specifications, you do not pay a price in the complexity. And this was quite surprising to us. Now, the coNP-hardness part is more or less immediate because, so the hard part of the proof is to show the upper bound, to show that this refinement problem can be solved in coNP. Or in other words, if something is not refined, then there is an NP algorithm to check that something is not refined. Now, this problem is quite difficult because you see this MPDA language on the left-hand side of the refinement problem is not necessarily complex, context-free. It can be actually a very complicated language. Okay, so let me just give some historical context. So what happens if you just have a single-threaded program that you model as a PDA? Well, there's an old algorithm by Knuth that shows that checking whether a PDA language belongs to the language of Dyck, the Dyck language with one kind of parenthesis can be solved in polynomial time. And only 40 years later, the inclusion problem of PDA in the general Dyck language was shown also to be in polynomial time. And there are interesting results along the way where this result in this polynomial time result was claimed, but the proof had a bug and so on. On the other hand, we cannot go much beyond Dyck languages. We do in the paper in a slightly more general class. But for example, if you try to replace Dyck languages by visibly pushdown languages, then that problem becomes undecidable. And similarly, instead of having PDAs, if you try to have order 2 pushdown systems, which are like higher order programs, you again get undecidability very quickly. Okay, so is this Dyck languages essentially because we can do it, or is there some external justification for using these specifications? Well, it turns out that there are a class of very commonly appearing patterns where the specification is given by Dyck languages. And this pattern is what is called reference counting. So imagine that you have a shared resource, and there are a bunch of threads that are accessing this resource. So what reference counting does is that, well, it keeps a counter with this resource that tracks how many threads are accessing this resource at any point. So when a thread makes a reference to this, holds a reference to this resource, you increase the counter. When a second thread comes, you increase the counter now to 2 because there are 2 references hanging around. Now, when the second thread is done, for example, you will reduce the counters to reflect the fact that only one thread has a reference. And when this thread is done, you will decrease the counter to 0. And when the counter is 0, you know that, well, you can just garbage collect this object because nobody is holding a reference. So this is a fairly general pattern that comes up in a lot of concurrent programs that share resources. And in particular, about 15 years ago, I wrote a paper about trying to solve these kind of reference counting problems through model checking. But at that point, we didn't really have an algorithmic way of approaching the problem, so there was a lot of manual intervention in trying to get the model checker to prove this. And I don't think you need to understand all that's going on in this code. So there's some shared resource, but what you need to understand are the events that show up in this kind of reference counting example. So the events would be things like increment a reference to an object. This would increment the counter. There is some assertion about availability of the resource. You want to make sure that when you're trying to access a resource, it's not garbage collected underneath you. And then at some point when you're done, you will decrement the reference count. And at some point, you might be checking whether the reference count is 0 in order to do your garbage collection. Okay, so in this program, you have these sequence of increments and decrements, and it turns out this program has a bug. And perhaps offline, you can try to think why this program has a bug. Okay. Right. So here are our events. We have increments, decrements, and 0 refs. Our goal is to ensure that the assertion holds. And essentially, the word that's generated by an execution is a sequence of increment and decrement operations and 0 ref operations. Okay. So for example, we want to make sure that the number of increments is greater than or equal to the number of decrements at any point. Okay, and that the counter is 0 when the program terminates. And this is not just the only example. In fact, Shaz and Dinghao Wu had a paper in 2004, which is kind of a prelude to all the work in context-bounded reachability, where they show some Windows device driver example, and essentially the crux of the problem there is also reference counting. Okay. So the way we do the reference counting is essentially having a letter for increment, having a letter for decrement, and think of these as opening and closing parentheses. And a valid trace is one where the increments and decrements form essentially a Dyck language. Now there's a slight detail in how you model the 0 reference. And it turns out that you can model 0 references by using a second kind of parenthesis. Right? So essentially imagine that you start by putting the second kind of parenthesis at the start of your program. Whenever you want to model that a 0 ref succeeds, you kind of close that parenthesis and open it again. And the point is that if the rest of the stack is empty, then you have this second kind of parenthesis that you can close. And then you put it back again to kind of revert to the situation that you have 0 outstanding counters. And if you want to model that the 0 ref returns false, well, the way you do it is that you close the bracket and open it. And this is only possible that if you had at least one open bracket. Okay. And again, this is not very important. The whole point is that we can take this reference counting example and we can model it as a problem as a specification that's given by a Dyck language. Okay. Okay. So this is essentially our modeling. And let me come back to the main result of this paper. Our goal is to show that this refinement problem can be done in coNP. So in order to, so we will, as I said, we will look at the opposite problem. We will say that if the refinement does not hold, then there is an NP algorithm that witnesses this. And essentially our proof will be a non-deterministic polynomial time algorithm that reduces to some NP oracle. And the first step is that we shall look at some properties of Dyck languages. And this is actually a very old result that says when is something not contained in a Dyck language? Well, when there are some kinds of violations. So the first violation is that if you have a word in your language which has a prefix where there are too many decrements, right? Too many things that are being closed, then this is not in the Dyck language because, well, you incremented something, let's say 3 times, and then you decremented it 4 times, right? And this we'll call a dip violation. Now, the other thing that can happen that causes you to not be in the Dyck language is that you have strictly more increments than decrements, right? Because then it's not a word in the well-balanced parenthesis because there is some increment, some open bracket that has not been closed. And we'll call this the offset violation. And finally, what can happen is that you can have an open bracket of one kind that you close with a closed bracket of a different kind. Okay? And this is what we call a mismatch violation. So the algorithm, the NP algorithm that we'll show is that given an MPDA and this parameter k, first we will check for offset violations, and this you can do in polynomial time. And then we will guess if there is a dip or a mismatch violation, assuming that there is no offset violation, and this we will do in NP. Now, the difficulty in the proof is that, well, we cannot really use the algorithms of Knuth or the polynomial time algorithm that checks PDAs are in a Dyck language, because the MPDA language need not be context-free. In fact, it can be very complicated. So the main idea of using the CFLs and saturation cannot be applied in our setting. In fact, we need to work with compressed word representations. We have to work with Spark images. In fact, I will show you that this proof is actually very complicated and uses a lot of these language theoretic techniques to get to the result. The second problem is that the usual techniques that we use in context bounded reachability does not work, because one of the key elements in all these proofs of context bounded reachability is that you kind of move things around. And you are allowed to do this because you're only looking at a regular setting. In our context, we cannot really summarize contexts and rearrange them. We really need to reason about when a particular letter is produced and what's on the stack at that point, because later on, this open bracket might be closed with somebody by a closed bracket in a completely different context with a completely different stack. And it turns out that we have to introduce new techniques related to vector addition systems to get this. And it turns out that the problems that we have are very close to problems that are long-standing open problems in the area, such as the problem of pushdown vast reachability. Okay, I will give you a very brief overview of the proof. So the first idea is that you take a trace of the concurrent or the multi-threaded program, and you can kind of decompose this trace into the trace of each thread. And it turns out that each of these threads, here the pink one or the blue one or the green one, represent context-free languages. So the trace is essentially, if you looked at the previous talk, it's an interleaving of these context-free languages. And the point is that because we fix k, there is a polynomial number of these context switch points, and we will just guess one of them, right? So we will guess what the context switch sequence is, and then we will work on it. And as I said, first we will look for offset violations. And for the moment, just assume that there's just one kind of bracket for offset violations. The same thing happens. It's an easy extension to different kinds of brackets. And what we'll do is that we'll use essentially an algorithm from the world of compressed words that allows us to compute the offset of a context-free grammar in polynomial time. And essentially, what we'll do is compute the offset for each of these grammars and then ensure that the total sum is 0. So this is essentially a small extension of known techniques. Similarly, for dip violations, what we'll do is we'll work with the Parikh image of the language and essentially use the result of Verma, Seidel, and Schwentig that says the Parikh image of a context-free language can be written as an existential Presburger formula, which is linear in the size of the grammar. And because existential Presburger arithmetic can be solved in NP, we again can check for dip violations in NP. Now, the mismatch violations turn out to be a very complicated algorithm. And I will not get into all the details, but I will tell you why this is non-trivial. So first of all, it's non-trivial because you have these open and closed brackets that are mostly okay, except for this one point where there is a mismatch. But this mismatch can be across different contexts of different threads. And so what could happen is that the open bracket in the mismatch happens at some point when a particular thread has a particular stack, and the closed bracket can happen in a completely different thread where there is a completely different stack. So the witness for a mismatch violation turns out to be a factor in a word where you have one kind of an open bracket, a different kind of a closed bracket, and a word in the middle. And this word essentially has the following form, right? So there will be some stack that goes up and down, but you know that this stack will never go below 0, and it will overall have an effect of 0. So essentially what we'll try to do is we'll try to find such factors. And one approach that we'll do is we'll use a counter to look for these kinds of U's in the middle and look for these mismatches. But the trouble, as I said, is that if you try to do this naively, then you get into these open problems of pushdown VAS reachability. And this is really open for a very long time. We don't know how to do this. So essentially what we'll do is that we have to come up with some new ideas. And it turns out that this is really the heart of the paper. Well, first of all, we show some combinatorial results that shows that we can break these runs into finite number of these polynomial number of run pairs. We can encode each VAS in each run pair with a two-dimensional VAS. And then we have to do some things with the VAS. Unfortunately, the things that we have to do with the VAS are p-space hard. So we have to come up with a new technique in order to avoid doing these things. So we do an annotation on the CFL and show that you can expand the language of the CFL while maintaining the property. And eventually, well, we will have to approximate these dips using some new results on Dyck languages, using some algebraic language theory, and so on. And eventually, well, we will get to some reachability of two-dimensional VAS, but which again is a very hard problem. So really, this was a Pilgrim's Progress kind of thing, right? So whenever we tried to do something, something else broke. But eventually, what we had to do is to introduce this new class of VAS called offset uniform VAS. And for that, we could show a reachability algorithm that runs in NP. So I don't want to get into the thing, but the proof is quite complicated. But overall, it shows that the complexity of this problem is no worse than the regular case. Now, of course, whenever something is NP, and usually when you reduce something to existential Presburger arithmetic, you might imagine that there is a pathway to implementations using SMT solvers. And this may be so, but we really haven't tried implementing this because the sequence of reductions is very complicated. That's it. And more or less, that's all I had to say. So as you can imagine, the new thing that we are looking at is that instead of having a fixed number of threads, can you also allow threads to be spawning new threads? And this turns out to be an even more difficult problem. Thank you for your attention.
Thank you, Rupak. Are there any questions? Okay, so there is one.
Thank you for the very nice talk, Rupak. So I have a question. What if that the trace is constructed on the fly? Have you considered the case, the dynamic case where, like, the model or the underlying trace are constructed on the fly, and does the result still hold, or what are how hard those problems are?
So we really haven't, I mean, we have only looked at this static setting, right? So where the model is given to you and you're doing a static analysis. I don't really know what it would mean. I mean, if you generate a particular trace on the fly, then of course I can take that trace and check if it belongs to the Dyck language quite easily, right? But the goal here is to say that every possible trace that this MPDA could generate belongs to the Dyck language, right? So So this seems to be a much harder problem, right? So yeah, given a trace, I can check if it's in the Dyck language. Right? So
Other questions? Okay, so this one here.
Hi, I'm Scott from University of Chicago. With your model of reference counting in the presence of multiple threads, how could you model things like atomic compare and swap and different things that you might need to ensure that you aren't running into the problem that you were showing on the screen before?
yeah, so I didn't get into this, but the model of MPDAs is and with shared state is actually quite general. So for example, you can have locks in your model, right? So you can model a shared Boolean variable that is kind of set in one atomic operation. So you can imagine that you have, I mean, as long as you have finite state variables, you have really all the kind of synchronization that you want, right? So
yeah, Arjun Radhakrishna from Microsoft. So this trick of adding another parenthesis, does it work when there are more than one things you're reference counting?
What we did was that we kind of projected onto each resource.
Okay, and separately check. Okay, thank you.
Do we have any idea of the expressivity of context-bounded languages with respect to other mildly context-sensitive languages, or is this different hierarchy?
Well, if I have a multiple pushdown machine, then you can get every recursively enumerable language, because two stacks already give you a Turing machine.
Mm-hmm. I see. I see. Thank you.
Other questions? So I have a question. What is the complexity of the naive deterministic algorithm for solving the same problem under context bounding?
Well, the deterministic algorithm would be exponential time, because
And the exponent would be in the k or the number of threads, or
this is a good question. So I don't know. So the deterministic algorithm I have in mind is that you take the non-deterministic one and just try every non-deterministic choice, right?
okay.
But this is probably going to be some multiple of k times the size of your program.
Okay. All right. Thank you.